Hello and welcome to this video on one of the most horrible ways to die. Neurotoxins. Okay, every way to die is horrible, but some are worse than others. As per Monty Python, death by considered good.
This man is about to die. In a few moments now, he will be killed. For Arthur Jarrett is a convicted criminal who has been allowed to choose the manner of his own execution.
Futurama has death by snoo snoo.
Visit Amazonia?
What'd they die of?
Crushed pelvises.
Yes!
Oh, thank you, Lord in heaven.
We could argue death by exorbitant donut feeding in The Simpsons is good. Death by K-pop is bad. And death by something that prevents your brain, spinal cord, or peripheral nervous system from working properly is especially bad. And possibly K-pop. The challenge is that no one thing is a neurotoxin. It is a collective term for a range of chemicals that all have a group of effects. Essentially, they can either affect developing or develop neurological tissue. For the purposes of this video, we'll largely focus on the kind that affects developed neurological tissue, just to understand that theoretically it can affect developing too. In very broad terms, we can split neurotoxins up into certain groups, although some neurotoxins may function across multiple groups, so this isn't a perfect way of defining them. You essentially have neurotoxins that will inhibit neuron function, receptor antagonists and agonists, those that are cytoskeleton interferers, multifactorial neurotoxins, and those that are endogenous. With that in mind, we should perhaps explain what most of these terms mean first. Inhibit means to stop the neuron from either sending out or responding to a signal. This is perhaps the easiest to understand. Next, we have agonists and antagonists. These can either block or overactivate the neuron. An agonist will activate the receptor that's attached to a neuron, and an antagonist will block the receptor. It's kind of how, say, an antagonist in any kind of TV show or similar will cock-block any of the other characters, whether they intend to or not. A toilet humor aside, it is perhaps the easiest way to remember this. Cytoskeleton interference is more complicated, particularly as a category, mostly because it involves literally changing the shape or structure of the neuron or cell. And much like the skeleton does for the human body, the cytoskeleton does for the cell. It keeps its shape and ensures it's mostly functional as intended. Multifactorial or multi-effect neurotoxins are the kind we mentioned earlier, where its mechanisms overlap with multiple other mechanisms. Lastly, we have endogenous neurotoxins. These are neurotoxins that, unlike just about everything else we will mention, are made inside your body, and typically inside the cell, or specifically the neuron. And this is essentially the body trying to poison itself. Ironically, many of these neurotoxins are actually useful and used in normal functions, but pose a threat when used incorrectly or generated in excessive quantities. We'll start with what is arguably the most basic, or at least most basic in that they affect one of the most fundamental parts of neurology. We have sodium channel inhibitors and potassium channel inhibitors. Both of these can largely be viewed in the same way. Understand, different neurotoxins will have different effects and block each of these individually, or possibly collectively, but the result is the same. That's because both of these have overlap in one very important function. They are both required for the action potential in neurons. More accurately, they're required to create the electrochemical gradient that will pass an action potential along the axon of a neuron. No action potential means no message gets sent. It's like a game of Chinese whispers, where someone in the middle just stops passing on the message. It means everybody after that hears nothing. This can also occur at the neuron body, where the receptors are located. By blocking the movement of potassium at the axon body, you get no receptor signal saying that the message was received. By blocking sodium at the axon end, you get no outbound signal saying that the message is being passed on. Essentially, you prevent the cell from being able to do anything. This can in turn prevent things like muscles from moving, which, given how important the diaphragm and heart are, and that they're made from muscles, you can imagine the dire consequences. You need your heart to pump blood around your body, and you need your diaphragm to move your lungs to oxygenate said blood. Not having that happen is generally adverse to life. This process, if depending on the drug in question that causes it, lead to a certain amount of pleasure. For instance, a tetrodotoxin, or essentially the poisonous product in pufferfish, is an example of it. It is why in small amounts the pufferfish is considered a delicacy. In larger amounts, it's considered deadly. Chloride channel inhibitors are the next, and in most respects they are very similar to both potassium and sodium channels. That is, they are largely related in many ways to the nerve itself, and like potassium and sodium, necessary for the neuron's communication and function. Essentially blocking either the outbound chloride or inbound chloride, you disrupt things like electrochemical gradients and the ability of the neuron to communicate. Calcium channel inhibitors are a little more complicated than this, and the primary complication is that calcium does a lot more in the cell, particularly the neuron, than just allow for the electrochemical gradient. They are, at least in part, involved with the action potential, but they also have other roles to play too, particularly when we talk about muscles. At the end of your axon, you have the axon terminal. This terminal will release calcium when it sends out a signal, a neurotransmitter. If you either prevent the release of calcium, or you prevent the neuron from recovering the calcium, it either slowly ceases to function, or doesn't function at all. In this case, the most common kind, or at least a candidate of this, is from cone snails. It's a particular chemical called conotoxin. It is named mostly after the fact that the conical shape of the shell. But what's important here is that the snail shoots out a little barb that has this toxin attached to it, and it will bind to specific neurons based on the presence of calcium channels. It means calcium channels may not release calcium, or worse yet, if they do, it won't be able to recover them, which is really unpleasant. Although unpleasant is a relative term. In theory, the slow loss of calcium is arguably a better scenario for you if you have some hope that you'll get, say, antivenom in time. And that's because it won't kill you, it'll just be very unpleasant, and you will recover. On the other hand, if you have no hope of being treated, perhaps a quick death is better. And next we have what every beautician, vain woman over 50, or man for that matter, a Kardashian and Hollywood celebrities' favourite toxin, particularly neurotoxin, botulinum. This is a kind of synaptic vessel inhibitor, and more specifically it inhibits the release of synaptic vessels, which is arguably slightly different. We mentioned how important it is to get the message to the end of the axon using an action potential. That is because you need the action potential to arrive and open various voltage-gated channels to let things like sodium or calcium move. This leads to the movement of vesicles filled with neurotransmitters towards the membrane, dock with the membrane, and then eventually release the neurotransmitter out of that membrane and into the area between neurons, called the synaptic cleft. These are what go on to communicate the signal between neurons. Peripherally, this is likely to be acetylcholine when we talk about botulinum, but other neurotoxins will have their own targets. For example, tetanus toxin is an example of something working in the central nervous system. But what we're talking about here particularly importantly is that you don't have the release of these neurotransmitters. In terms of the peripheral nervous system, this leads to relaxation of the skin, which is why you get that smooth appearance, and possibly death if they screw up the dosage. In the case of tetanus, it's central nervous system and it prevents muscle control, leading to constant muscle spasming, or at least uncontrollable spasming, and no ability to relax those muscles. The key thing here is that if you do not release neurotransmitters, there is no communication between neurons. They ghost each other like a bad Tinder date. And so, this is why things like botulinum toxin and tetanus toxin are both examples of neurotoxins. The next thing we're going to look at is the central nervous system on a larger scale, but we're looking at the outside of it, the blood-brain barrier. And this is where certain blood-brain barrier inhibitors are going to be important. It's also where things start to get more complicated again. It's because the blood-brain barrier is not just complicated, but large. And it has several layers to it, but for the purpose of this video, we'll just focus on what the toxins are doing for the most part. Examples are going to be things like aluminium and mercury, although it should be noted that we're talking here about ionic aluminium and essentially pure mercury, so you don't need to get excited about it just yet, as these things rarely occur in isolation unless you're exposed to them in a toxic way. Or you piss off Vladimir Putin. It's possible that he may decide that you're no longer a person. And most of the time, you will need both high levels, long duration, and some sort of comorbidity to see the neurotoxic effects of these particular neurotoxins. And it's more important again for aluminium, where mercury is somewhat faster acting, so to say. The effect of aluminium is that it reduces the blood-brain barrier's ability to function as a barrier. This only occurs though if you get aluminium in ionic form. That means the aluminium as an adjunct, part of a large compound, etc. will not be neurotoxic. It essentially has to be a pure aluminium. Not dialuminium, so it's bound together, or in some other similar complicated bigger structure, but pure aluminium. Mercury is rather more clear, and this is because rather than just essentially making the blood-brain barrier fail, mercury will affect the neurons themselves. What it does is it prevents the function of amino acids and glutamate transport, or more accurate to say, the transport of amino acids and glutamate. Amino acids on a larger scale are needed not just for cell function and repair, but to be used in the production of various cell components. Glutamate is an amino acid itself, but unlike the others, it is also needed and used as a neurotransmitter that excites neurons or increases their activity. This is where mercury is dangerous as a neurotoxin. It essentially prevents the activation and excitation of certain neurons through a neurotransmitter. By contrast, let's say, to the excitation of neurons, we have inhibitors or antagonists. Although, strictly speaking, it's more accurate to say that they push against the default position of the neurons. So, let's say the neuron is always in the on position. Well, if you have an antagonist, it's trying to put it to the off position. This is where and how receptor inhibitors or antagonists are particularly relevant. An example is curare. It's a blow-dart poison used by certain tribes. What they do is they interact with the nicotinic acetylcholine receptors. Now, what's important here is that these are a smaller receptor family under the GABA family. By targeting these, you begin to interfere with ion channels. These are things like the potassium, calcium, sodium, and so on ion channels. And because they don't work the way they're intended to, you now have problems with things like, for example, action potential. Typically speaking, what you would normally have is something like acetylcholine binding to its receptor. Now, this is found in the postsynaptic neuronal membrane, essentially the neuron on the other side of that synaptic gap. We then see a change occurring in that receptor, and this leads to a series of cascading changes that then open up those ionic channels. This allows, for example, sodium to pour in or calcium to pour in. This would ideally lead to depolarization, and you begin the process of sending a action potential down the axon. This is in the ideal scenario. The problem with this is that, well, with things like curare and similar, you get that binding, but it's not a temporary binding, it's an irreversible binding. This means that in terms of at least those receptors, the ion channels are now permanently closed. They cannot be opened. That means no matter how many signals you send, you will be stuck on message red. Okay, enough bad tinge jokes, but still, this is essentially what happens. You get in a situation where you can no longer activate that part of the neuron. Receptor agonists, on the other hand, will essentially do the opposite. They promote an activity. They push more heavily on that side of the scale, causing an increase in a specific cell functional role. Anatoxin alpha is a good example of this, although there are others, and what they do is essentially the opposite. Rather than binding to that receptor and blocking it off and preventing it from ever being activated, they instead bind to it permanently and then leave those ionic channels open permanently. This, for all intents and purposes, overstimulates that particular neuron, and eventually it just fizzles out and dies. It's a slight oversimplification, but understand, leaving those ionic channels open permanently leads to all sorts of problems. For example, you could have too much water trying to enter the neuron due to osmosis, causing them to lyse, and there are other ways again. Now we have the actual neuron itself. If we look back at it, structurally, it's fairly straightforward. You essentially have a body with a whole bunch of dendrites coming off of it that are where you find your receptors. You have a long tail-like structure, and at the end of this, you have the end of what is called the axon being that long tail-like structure. You need to get a signal from the body, which is a large bulbous part with all the dendrites attached to it, down the axon and to the end of it. In order to have this structure, it needs a skeleton. But what happens when you start interfering with that skeleton? Well, that's where some neurotoxins that do exactly that cytoskeletal interference, neurotoxins come into play, ammonia and arsenic being examples of this. The results are not pleasant to say the least. In short, for the most part, you find that they can no longer maintain their shape, which is not good. You typically need a neuron, and for that matter any other cell, to be the shape it is for a very good reason. One of the most obvious and simple effects is going to be something like, say, edema or swelling in the area, and then consequentially you get lysing from osmosis, which is water entering the cell. The other issues can be things like metabolism no longer works as it's intended to. The fact that you no longer have that nice simplified structure, admittedly oversimplified, where you have an action potential passing down the axon. Perhaps it can no longer do that until it loses its function. And there are other ways again where simply no longer having the right shape will be a problem. Imagine the shape of the ball in your preferred sports ball. Whether it's a football, a soccer ball, a cricket ball, a baseball, or whatever it is. And now imagine if you had to change the shape of that ball, how well would that particular sports ball work for you? Probably not very well. Next we have calcium-mediated neurotoxins, and the best example of this will and perhaps always be lead. The reason this works so well as a neurotoxin is that lead essentially has a way to be mistaken for calcium for neurons. We mentioned earlier how neurons both put out calcium and need to recover it. Well, if you're recovering, at least in the case of a neuron, what you think is calcium, but turns out to be lead, you have problems. One of the issues you're going to find is that if you unfortunately take up lead instead of calcium, you get a whole bunch of cascading processes that no longer work because they don't have what they need. They don't have calcium. You also have issues around apoptosis being initiated because of that. And of course, apoptosis for neurons is, well, frankly, bad. On top of all of this, which is perhaps the cherry on the shit sandwich that we have so far with lead poisoning, essentially, is that even if it doesn't kill you and doesn't cause much harm, it can still interfere with the ability of neurons to work, and that's because you need calcium to do various things, particularly when it comes to neurotransmitter release. A calcium that's no longer available because you took up lead instead. Yeah. Lead really only sends a message if you're shooting at someone, or if you're American school children in Flint. And that's because occasionally, at least in America, they're the same thing, particularly when we talk about Flint, Michigan. Next we have protein misfolding. Now this is essentially the same sort of thing you'd see as, say, Alzheimer's disease, and we can pretty much use the standard example here, which is tau proteins. Tau protein bundles to be more exact, and they are more like an inhibitor in some ways to neuron functioning, but they really do cover a range of possible areas here as they overlap in multiple ways, and one of the best ways to explain this is that they can interfere with things like action potential, thereby preventing the transmission of that action potential along the axon. In other cases, they change the cytoskeleton of the neuron, leading to all sorts of issues around that, and they are a great introduction to how you can have multiple effects, because all you've essentially done is stuff up the proteins within the neuron, and suddenly you begin to see all sorts of complications. Perhaps the best and tried and true example of this multiple effect mechanism is ethanol. Yeah, ethanol, well, we'll be clear about this. Ethanol in most adults is going to cause some of these issues, but ethanol, particularly if we're talking about, say, fetal alcohol syndrome, is going to be far more pronounced as it has these effects, but on a much larger scale. So it's going to do things like, say, damage the cellular membrane, leading to all sorts of issues around the release and particularly concentration of various parts of it. So if you don't have the necessary components, you can't release neurotransmitters, or in other cases, you can't receive the signal necessarily from neurotransmitters from other neurons that are otherwise unharmed. Those vesicles may not be transported. You may not have the necessary network functioning, so although you might get a localized communication of something, further out from there, it just doesn't happen. And there are a variety of other ways that it can have multiple effects. Now, we've talked about everything so far on a large scale, and that's because most of this has not been very specific to one part of the brain, but there are arguably parts, or at least some types of neurotoxins, that are more specific, and that's because they only target certain receptors. These are called, unimaginatively, receptor-selective neurotoxins. Now, the go-to example is going to be MPP+, which we're not going to bother with the name. It's complicated and it's not overly important, but what it does is it interferes with how the mitochondria deals with things like oxidative phosphorylation. And because of that, you get issues around ATP not being generated. No ATP means no cell energy, cell death follows. The key thing though is that, for the most part, the things it's targeting here are not located consistently throughout parts of the body. And so, in the brain particularly, exposure to this can actually lead to symptoms within a few days. That's how specific and how extensive in that area the damage is. In fact, it can take as little as 2 to 3 days after administration of MPP+ to see this effect. And now we go on to the body's own attempt to do something stupid, because the human body can always do better, just not in ways we want. These are what we call endogenous neurotoxins. Endogenous neurotoxins are essentially things that are commonly used in the body and often intended to be used in the body, but unfortunately, when things go wrong, they begin to cause damage, and quite a bit. There are two we'll talk about for now, nitric oxide and we have glutamate. Now, both of these sound like they should be fairly familiar if you know much about the human body. Nitric oxide is used a lot in cell communication. One of the big things it does is it causes blood vessels to dilate. This allows for blood flow to go through more easily, which is great if, for example, you're having a heart attack, or if you're stressed. However, if you have nitric oxide and it's delivering more blood to certain parts of the brain, it can actually cause oxidative damage. That's because, as the name would suggest, it's a nitric group, which is sodium and an oxygen. Theoretically, this can grab onto all sorts of things and cause damage. So you have oxidative stress, and you can further to oxidative stress and cause damage to the DNA. Again, oxygen is something nasty at times. And of course, once you start damaging cells, DNA and everything else, the body goes, we give up, and it commits apoptosis in the form of cell death. It's very much like the crack suicide squad of the GA and People's Front in Monty Python's Life of Brian. One of the more, let's call it almost insidious examples is glutamate. Now, glutamate, as we've mentioned earlier in the video, is an excitatory neurotransmitter. That is, it's supposed to make neurons more active in what they're doing. However, that's only when the concentrations are controlled and appropriate to the circumstances. If the concentration starts to go up, you have a problem. Glutamate becomes toxic to neurons at that point, and it can lead to the death of those neurons. It is essentially poison at that point. The way it works is simple enough. You get calcium trying to flow into the cells to which it's sending a signal, at least incorrectly sending a signal. Because you now have a massive influx of calcium into these neurons, you also have water following, and water follows and follows and follows and follows until those neurons swell and then die in a process of necrosis, which is uncontrolled cell death. As you can see, neurotoxins are not just diverse, but they don't always require an external source. Fortunately, most of the time, they do. Unfortunately, the source is likely to lead to you having a very bad time before you die very soon after. And if you don't die soon after, there's a modest chance you'd wish you had. Thank you for watching this video. If you have found it interesting, consider liking, sharing, and subscribing. And please do post any comments, questions, or suggestions you have below.